Hello, everyone. Welcome back to my YouTube channel. Today, we're going to look into a new paper called You Better Pay Better Attention: Rethinking the Mathematics of Attention Mechanism. Well, this paper is, from my understanding, about a new attention mechanism that they propose in the paper that tries to deal with the existing problems with the original attention mechanism. Before we get started, I would like to let you know that you can like, comment, and subscribe on my videos if you find it to be okay to do so, and that would support my future videos as well. So yeah, okay, let's get right into it. First of all, let's go through the abstract together, shall we? Right. Scale dot product attention, the original attention mechanism, is the backbone of many modern deep learning models. It is versatile as it has been used in NLP, vision, and multimodal domains with very little change compared to its original formulation. Well, this is technically true, right? Even the entire transformer architecture hasn't really changed that much over a lot of years back then. Okay, this paper discusses why the current formulation is inefficient, right? By delving into the mathematical details. Wait, by the way, it says delving. Kind of sounds like a chat GPT's writing, but anyway, right. Delving into the mathematical details of the attention mechanism, they propose three new improvements to handle these efficiencies, introducing three enhanced attention mechanisms: optimize, efficient, super attention. Optimized and efficient attention have one and two matrix multiplications fewer per head. Okay, that's important. And 25 and 50% fewer parameters, cool, respectively, than the standard scale dot product attention, but performs similarly. Right. So I bet what they're trying to say is that the accuracy, there's not much of an accuracy drop in with their approach. Okay, and they tested it out on both the vision and the NLP tasks, which we will get into in a second. They can be used in all applications where scaled up product attention is used while offering smaller model sizes and faster training and inference without no noticeable loss in performance. But I bet the loss in performance is still there regardless, right? I mean, that's kind of what a lot of papers back in the day. I'm not so sure if you remember this, but have you heard about efficient attention mechanisms? Yeah, things like linear attention that have been shown to work great for like a certain model size, but as you try to scale them up to like 7 billion parameters, their accuracy drop is quite large. So I'm not so sure if they will test it out on large model training, but let's see later. Okay, right. I think so. Let me see. More general formulation, one can use different A to perhaps gain better performance. Well, yeah, but at the cost of increasing parameters. Okay. So this is their final ultimate omega super attention. Right. So let's see. So they have so they have Q as usual, Q prime, and now they have this one right here, WA followed by VI. As you can see, one thing that's interesting here is that WA is right on the left hand side. While if you take a look at W cubed, it's on the right hand side, right? So if we do some matrix shape multiplication, right? Let's say if this is that, right? So I mean, it's it's just gotta be that. Well, this one right here, this is the one, right? I mean, yeah. I mean, it makes sense, right? Hmm, okay. Hmm. Hey, why can't I erase that? Oh well. Anyway, right. So and the shape is R L times L. The alignment kernel. Okay, so it has a name. The A stands for alignment, which vertically, for the values corresponding to different tokens, aligns and mixes the values before the attention scores are applied to them. Okay, right. Look, I think this one is more interesting than the other variants that we looked at so far, right? Just a simple alignment kernel makes a lot of difference from their point, but we shall see. Okay, right. Right. Super attention is more efficient than normal attention when the model dimension dm is greater or equal to the context length. This means that super attention has at least H matrix multiplication and dm to the power 2 parameters fewer than standard attention. Okay, we're not going to look at the proof because this is not uh, what we're going to do right now. Instead, we're going to look at the results, right? And this is the most important part, right? You can have beautiful methods, but if it doesn't produce any kind of like meaningful improvements, then it's not really worth talking about or even using, right? Now let's go through it. So, okay, let's do this. Evaluation methods. We have choose benchmarks that are easy and fair comparisons between the four attention mechanisms. Okay, the four being the ordinary attention, the and their proposed three types of attention mechanisms, right? But I think it would be better if they could like include other attention variants as well. Yeah, but that's just me saying, Okay, okay. Right. Next, in each experiment where we have used a code from an online resource, we have minimized the changes to the original code to ensure the fairness of our comparisons. Okay, right. I see. I mean, yeah. I mean the yeah. It depends. The comp- the computational cost also comes from how well you write the code. So I guess yeah. Try to control that for this experiment. Okay, for all experiments, we use the same model architecture and iterate between standard, optimized, efficient, and super attention. We use smallest model sizes that yield meaningful results to ensure maximum utilization of the attention mechanism. We continue training until validation loss flattens, which we have observed to be approximately the same among all attention mechanisms. We report the results by averaging over 5 runs, except for ImageNet, due to the large dataset, and we report the results over one training. Okay, okay, this is good, right? Right. In that case, right, right, since their accuracy is so great, right, I wouldn't even call it like on par. I would just say like better performance on average, right? It's actually better while being faster as well. Yeah. You know what? Yeah, I take my words, right? I think this paper could be useful, right? And I certainly will consider it for my own research paper as well. But yeah, yeah. So there's a lot more data here, a lot more supplementary information here. But I'm not gonna go through them. I will probably read those things on my own. But yeah, I hope you guys like my video. Yeah, and don't forget to like, comment, and subscribe. And I will see you all in the next video.